Hello, this is Captain Chaudhari. Today I want to speak about the planets in my videos, in the series of videos on marine astronomical navigation. Today I want to talk about planets, solar system actually, but generally about the planets. And when we talk about planets, you cannot ignore Kepler's laws of planetary motion. Kepler's three laws of planetary motion are very important to understand the relative positioning of the planets, their motion in the orbit, etc. Now, before we learn Kepler's laws, let us understand what is ellipse. Ellipse is a trace that is described by a pencil, right? It is described by a pencil, but around the pencil, I'm going to tie up a string, a thin string, and I take the pencil round in such a way that both the parts of the string are taut at all times, which means that if there are two foci, focus 1 and focus 2, the sum of distances d1 and d2, d1 plus d2 is always constant. d1 and d2 is always constant. That means if I take the pencil over here, then the total distance d1 plus d2 is same as this distance d1 plus d2. So this is ellipse. So ellipse is locus of a point moving in such a way that the total distance, the combined distance from the two fixed points, the foci, is constant. Now if this is the ellipse, when we say this is the major axis, this is the minor axis, this is focus 1 and focus 2. This is called the major axis of the ellipse and this is called the minor axis. Now, let us now talk about the Kepler's laws. Kepler has three laws. The first law of motion is all the planets, they revolve around the sun, with sun located at one of the foci. I mean, sun is not in the center of ellipse. Sun is there on one of the foci. And these planets, when they revolve around the sun, naturally, if the sun is not in center, it's at one of the foci, sometimes the planet is going to be nearest, so this is called perihelion. And at some other time, the sun is going to be furthest, it is called aphelion. So all these planets, they are exposed to perihelion and aphelion. Meaning of helion is sun, in reference to Earth. Right now the sun is in perigee, and when the Earth comes over here, the sun is in apogee. Otherwise also, if you observe the diameter of the sun, there is a month during which the diameter of the sun is maximum. That would probably happen on perihelion. And there is another time when the diameter of the sun would be minimum. That would be aphelion period. So this is the first law of motion. Now the second law of motion is when the Earth or any planet moves around the sun, there is a time when the speed is maximum, right? And then there is another time when the speed is minimum. But how you describe it by the second law? It says that the radius vector, right, describes equal area in equal time. So if we say that while the planet moves from here to here, right, this period, if it is same as this period, then this area described by the radius vector over here would be same as the radius vector's area over here, and likewise in any other position. So wherever the planet goes, wherever the Earth goes, it will describe the same radius vector, which also means that when the Earth is closest to the sun, the speed is maximum. The speed is maximum, and when the Earth is furthest away from the sun, the speed is minimum. The linear speed is minimum. This is to satisfy the second law of motion. This also means that when we talk about the relative speed of true sun on ecliptic, actually, as we know that Earth goes around the ecliptic, if you consider this as ecliptic, plane of ecliptic, Earth goes around the ecliptic, right? And therefore, as a relative motion, as an annual relative motion, Like if you take the video of the sun, and if you could see the sun against stars, then you would be able to make out that sun moves from one constellation to another constellation. And if you fast forward this motion of sun, taken through the year, 365 days, and there are stars in background, you will find that the sun moves in the sky from one constellation to other, from one house to other house. And this movement on this giant great circle called ecliptic, this motion is eastward, and this is the annual motion. Now this eastward annual motion that I'm talking about, the true sun would appear, the sun would appear to move fastest when at perihelion, and when Earth is in perihelion, and it would show the sun's linear speed on ecliptic, the relative speed of the sun, relative annual speed of the sun, slowest at perihelion. Now the spinning of the Earth is also associated with the duration of day, the lunar day, solar day, and sidereal day. In the orbital motion of the Earth, or revolution of the Earth around the sun, if the sun is moving at a different linear speed, it would probably affect the duration of day also. That we will see a little later on. But at the moment, let us talk about the third law. As I told you, this is the major axis and this is the minor axis. So half of the major axis should be the semi-major axis. So all the planets which are there in the solar system, all these planets, we can say that they have a certain semi-major axis. Now, what is the relationship? The relationship is t square upon d cube is fixed for all the planets, and t is the sidereal period. T is the sidereal period means with the star as a referee. Suppose there is a star over here. With the star as a referee, when does this Earth complete a revolution around the sun? That is the sidereal period of revolution of Earth, or any planet for that matter. So that sidereal period which is there, the period of revolution with star as a referee, right? And d is the distance along the semi-major axis. That means in case of Earth, this is the distance, semi-major axis. So for each planet, whatever is the sidereal period, square of that, whatever is the distance along the semi-major axis, the cube of that, this ratio is fixed. So that is the third law. This straight away means that all the planets which are closer to sun, they will be faster than the planet which is further off. Mercury being closest to the sun, and the second one is Venus. Now these two planets will have orbital period less than the Earth's orbital period. And then Jupiter, Saturn, and all the other planets which are having the orbit outside the Earth's orbit, whose orbital distance from the sun is more than that of the Earth-Sun distance, they will have a period more than the Earth's period. So as you go away from the sun, your period of revolution increases more and more. Like in case of Jupiter, the period is 11.86 years, and the period is 29.4 years in case of Saturn. Whereas in case of Venus, which is a minor planet, right, the period is just about 224 days. It is 88 days for Mercury.